perform load calculations for electrical design, there's a recommended process to follow. Software provides the best method for an architect. Dedicated load calculation software designed specifically for architects simplifies the process and provides accurate results. Examples of such software are Write Suite, ETAP, or GE Panel Builder. The NEC, or National Electrical Code, does provide general guidelines for load calculations, but it does not offer a specific procedure tailored for architects. The book Electrical Calculations Handbook by Ed Holt provides comprehensive procedures and formulas for electrical calculations. However, it is intended for engineers and may be challenging for architects without a strong engineering background. A recommended procedure for performing load calculations involves these steps. Firstly, you should gather building information. Determine the building type, occupancy, area, and heating and cooling systems. Secondly, use load calculation software. Input the gathered information into a load calculation software. The software will apply the appropriate calculation methods and provide a detailed breakdown of loads. Thirdly, review and adjust results. The software results should be reviewed for accuracy. Adjust any assumptions or parameters as necessary. Fourthly, coordinate with an engineer. If the project requires a signed and sealed electrical design, it is recommended to consult with a licensed electrical engineer for verification and approval of the load calculations. Some additional tips to consider include: firstly, using an architect who has experience in electrical load calculations. Secondly, attending a training course or webinar on electrical load calculations specifically for architects. And thirdly, utilizing online resources and industry forums for support and guidance. By following these steps, architects can effectively perform load calculations for electrical design, ensuring the safety and functionality of their projects. Calculating electrical loads is a critical aspect of designing a safe and efficient electrical system for any building. It involves determining the total amount of electrical power that a building or a specific part of a building is expected to consume. This information is then used to select the appropriate size of electrical service, wiring, circuit breakers, and other electrical components. The process typically begins with identifying all the electrical loads within the building. These loads can be categorized into different types, such as lighting, receptacles, appliances, HVAC systems, and motors. Each load has a specific power requirement, usually expressed in watts or voltamps. To determine the total load, you need to consider both the continuous and non-continuous loads. Continuous loads are those that are expected to operate for 3 hours or more at a time, while non-continuous loads are those that operate for less than 3 hours. The NEC requires that continuous loads be multiplied by a factor of 1.25 to account for the additional stress they place on the electrical system. After identifying and categorizing all the electrical loads, you need to apply demand factors to account for the fact that not all loads will be operating at the same time. Demand factors are percentages that are applied to the total load to estimate the actual amount of power that will be consumed at any given time. The NEC provides tables of demand factors for different types of occupancies and loads. Once you have calculated the total demand load, you can use this information to select the appropriate size of electrical service, wiring, and overcurrent protection devices. The electrical service is the main connection between the building's electrical system and the utility grid. The size of the electrical service is determined by the total demand load and the voltage of the electrical system. The wiring must be sized to carry the expected current without overheating. The NEC provides tables that specify the ampacity of different types of wires based on their size and insulation. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the wiring from overloads and short circuits. The size of the overcurrent protection devices must be matched to the ampacity of the wiring. In addition to the general load calculation procedures outlined above, there are also specific requirements for certain types of loads, such as motors and HVAC systems. Motors, for example, require special consideration because they draw a large amount of current when they start up. The NEC provides rules for calculating the motor starting current and for selecting the appropriate size of overcurrent protection devices. HVAC systems also require special consideration because they often have multiple components such as compressors, fans, and heaters. The NEC provides rules for calculating the total load of an HVAC system and for selecting the appropriate size of electrical service and wiring. Accurate load calculations are essential for ensuring the safety and reliability of an electrical system. Overestimating the load can lead to unnecessary expense, while underestimating the load can lead to overloaded circuits, overheating, and even fires. Therefore, it is important to follow the NEC guidelines and to consult with a qualified electrical engineer if you have any questions. Choosing the right software for electrical load calculations depends on your specific needs and the complexity of the projects you typically handle. Several software options are available, each with its own strengths and weaknesses. Some popular choices include firstly, Right Suite Universal, which is a comprehensive software suite that includes load calculation, dock sizing, and energy analysis tools. It is well suited for residential and light commercial projects. Secondly, EHAP, which is a full-spectrum analytical engineering software for the design, simulation, operation, and automation of power systems. It is widely used for large-scale industrial and commercial projects. Thirdly, GE Panel Builder, which is a user-friendly software for designing and configuring electrical panels. It includes load calculation features and helps ensure compliance with NEC standards. Other options to consider include Easy Power, SKM Power Tools, and Electrical Designer. When evaluating software, consider the following factors. Firstly, ease of use. The software should be intuitive and easy to learn, even for users with limited experience in electrical design. Secondly, accuracy. The software should provide accurate and reliable results that comply with NEC standards. Thirdly, features. The software should include the features you need for your specific projects, such as load calculation, panel design, and voltage drop analysis. Fourthly, cost. The software should be affordable and offer a good value for your money. Fifthly, support. The software vendor should provide good customer support and training. Ultimately, the best way to choose the right software is to try out a few different options and see which one works best for you. Many software vendors offer free trials or demos. Understanding the roles of the NEC and other resources like Holt's book is crucial for accurate and compliant electrical load calculations. The NEC, or National Electrical Code, is a set of standards for safe electrical design, installation, and inspection. It is updated every 3 years and is widely adopted in the United States. The NEC provides general guidelines for load calculations, but it does not offer a specific procedure tailored for every type of project. It is important to consult the NEC for specific requirements and to ensure that your calculations comply with the latest edition. Holt's Electrical Calculations Handbook is a comprehensive resource that provides detailed procedures and formulas for electrical calculations. It covers a wide range of topics, including load calculations, voltage drop calculations, and short-circuit calculations. However, it is primarily intended for engineers and may be challenging for architects without a strong engineering background. Other resources that can be helpful for electrical load calculations include firstly, online calculators. Several websites offer free online calculators for performing basic load calculations. These calculators can be useful for quick estimates, but they should not be used for final design calculations. Secondly, industry forums. Online forums and discussion groups can provide a valuable source of information and support. You can ask questions and get advice from experienced electrical professionals. Thirdly, training courses. Many organizations offer training courses on electrical load calculations. These courses can provide a more in-depth understanding of the subject and help you develop the skills you need to perform accurate calculations. It is important to remember that electrical load calculations can be complex and require a thorough understanding of the NEC and other relevant standards. If you are not comfortable performing these calculations yourself, it is best to consult with a qualified electrical engineer. Coordinating with a licensed electrical engineer is essential for ensuring the safety and compliance of your electrical design. The electrical engineers have the education, training, and experience necessary to perform accurate load calculations and to design electrical systems that meet all applicable codes and standards. They can also provide valuable insights and recommendations to help you optimize your design and reduce costs. In many jurisdictions, a signed and sealed electrical design is required for certain types of projects, such as commercial buildings and large residential projects. This means that a licensed electrical engineer must review and approve the design before it can be submitted for permitting. Even if a signed and sealed design is not required, it is still a good idea to consult with an electrical engineer to ensure that your design is safe and compliant. An electrical engineer can help you firstly perform accurate load calculations. Secondly, select the appropriate size of electrical service, wiring, and overcurrent protection devices. Thirdly, design a safe and efficient electrical system. Fourthly, ensure compliance with all applicable codes and standards. And fifthly, identify potential problems and recommend solutions. When choosing an electrical engineer, look for someone who has experience with similar types of projects and who is familiar with the local codes and standards. You should also check their references and make sure they are properly licensed and insured. By working with a qualified electrical engineer, you can ensure that your electrical design is safe, compliant, and meets your specific needs. Understanding general occupancy loads is fundamental to accurate electrical load calculations. Different types of buildings and spaces have varying electrical demands based on their intended use and the activities that take place within them. The NEC provides specific guidelines and requirements for calculating these loads, ensuring that electrical systems are adequately sized to handle the expected power consumption. Firstly, dwelling units. For residential buildings, the NEC specifies a minimum general lighting load based on the square footage of the dwelling. This load covers general illumination and receptacle outlets for general use. Additional loads must be calculated for appliances, heating, and air conditioning systems, and other specific equipment. Secondly, commercial buildings. Commercial occupancies, such as offices, retail stores, and restaurants, have diverse electrical needs. The NEC provides different load calculation methods based on the type of business and the equipment used. General lighting, receptacle outlets, HVAC systems, and specialized equipment like cooking appliances or machinery all contribute to the overall load. Thirdly, industrial facilities. Industrial buildings often have high electrical demands due to heavy machinery, specialized equipment, and extensive lighting systems. Load calculations for industrial facilities must consider the specific equipment used, its operating cycles, and any potential future expansion. Fourthly, institutional buildings. Schools, hospitals, and other institutional buildings have unique electrical requirements. Load calculations must account for lighting, HVAC systems, medical equipment, and other specialized systems. Emergency power systems are also critical in these facilities, requiring careful consideration during load calculations. Fifthly, assembly occupancies. Buildings used for public gatherings, such as theaters, auditoriums, and churches, require specific electrical systems for lighting, sound, and stage equipment. Load calculations must consider the potential for large crowds and the need for reliable power to support these activities. In addition to these general occupancy types, the NEC also provides specific load calculation methods for various specialized loads, such as motors, transformers, and electric welters. Accurate load calculations are essential for ensuring that electrical systems are safe, reliable, and capable of meeting the demands of the occupancy. Consulting with a qualified electrical engineer is recommended for complex projects to ensure compliance with the NEC and best practices. Furthermore, understanding demand factors can help optimize electrical load calculations, particularly in large buildings with diverse loads. Demand factors are multipliers applied to the total connected load to estimate the maximum amount of power that will be used at any given time. This is based on the understanding that not all electrical equipment will operate simultaneously at its maximum capacity. The NEC provides tables of demand factors for various occupancy types and equipment, allowing for more accurate sizing of electrical services and distribution equipment. Firstly, residential demand factors. In dwelling units, demand factors recognize that not all appliances and lighting fixtures will be on at the same time. The NEC allows for reducing the total connected load based on the number of appliances and the size of the dwelling. Secondly, commercial demand factors. Commercial buildings often have diverse loads, including lighting, receptacles, HVAC systems, and specialized equipment. Demand factors can be applied to each of these loads based on their usage patterns. For example, lighting loads may have a demand factor of 1.0, while receptacle loads may have a low demand factor due to intermittent use. Thirdly, industrial demand factors. Industrial facilities with heavy machinery and equipment may have complex load profiles. Demand factors can be applied to different types of equipment based on their operating cycles and the likelihood of simultaneous operation. Fourthly, HVAC demand factors. Heating, ventilation, and air conditioning systems can contribute significantly to the overall electrical load. Demand factors can be applied to HVAC loads based on the climate, building insulation, and occupancy patterns. Fifthly, feeder and service demand factors. The NEC allows for applying demand factors to feeder and service conductors based on the total connected load and the occupancy type. This can result in significant cost savings by reducing the size of conductors and equipment required. It is important to use demand factors carefully and to consider the specific characteristics of the building and its occupants. Overly optimistic demand factors can lead to undersized electrical systems, while conservative demand factors can result in unnecessary costs. Consulting with a qualified electrical engineer is recommended to determine the appropriate demand factors for a given project. Moreover, calculating feeder and service loads accurately is crucial for ensuring that electrical systems can safely and reliably supply power to all parts of a building. Feeders are the conductors that carry power from the service entrance to individual branch circuits or subpanels, while the service is the main connection between the building's electrical system and the utility grid. The NEC provides specific guidelines and requirements for calculating these loads, taking into account factors such as occupancy type, connected loads, and demand factors. Firstly, determining the connected load. The first step in calculating feeder and service loads is to determine the total connected load of all the electrical equipment that will be served. This includes lighting, receptacles, appliances, HVAC systems, and any other electrical devices. The connected load is typically expressed in volt-amps or watts. Secondly, applying demand factors. Once the connected load has been determined, demand factors can be applied to estimate the maximum amount of power that will be used at any given time. The NEC provides tables of demand factors for various occupancy types and equipment, allowing for more accurate sizing of feeders and services. Thirdly, calculating the feeder load. The feeder load is calculated by multiplying the connected load by the appropriate demand factor. This value represents the maximum amount of power that the feeder is expected to carry at any given time. The feeder conductors must be sized to handle this load without overheating or causing excessive voltage drop. Fourthly, calculating the service load. The service load is calculated by summing the feeder loads for all the feeders that are connected to the service. This value represents the total amount of power that the service is expected to supply to the building. The service conductors and equipment must be sized to handle this load without overloading or causing voltage problems. Fifthly, considering future expansion. When calculating feeder and service loads, it is important to consider the potential for future expansion. The electrical system should be designed with enough capacity to accommodate any anticipated increases in load. This can be achieved by oversizing the feeders and services or by providing spare capacity in the electrical panels. In addition to these general guidelines, the NEC also provides specific requirements for calculating feeder and service loads for certain types of equipment, such as motors, transformers, and electric welders. Consulting with a qualified electrical engineer is recommended for complex projects to ensure compliance with the NEC and best practices. Furthermore, Addressing voltage drop considerations is essential for maintaining the performance and efficiency of electrical systems. Voltage drop occurs when the voltage at the end of a conductor is lower than the voltage at the source due to the impedance of the conductor. Excessive voltage drop can cause equipment to malfunction, reduce lighting brightness, and increase energy consumption. The NEC provides guidelines for limiting voltage drop in branch circuits and feeders. Firstly, understanding voltage drop. Voltage drop is caused by the resistance and reactance of the conductors in an electrical circuit. The longer the conductor and the smaller its cross-sectional area, the greater the voltage drop will be. The amount of current flowing through the conductor also affects the voltage drop. Secondly, NEC voltage drop limits. The NEC recommends that voltage drop in branch circuits should not exceed 3%, and voltage drop in feeders should not exceed 5%. The total voltage drop from the service entrance to the furthest point in the branch circuit should not exceed 5%. Thirdly, calculating voltage drop. Voltage drop can be calculated using various formulas and online calculators. The calculations take into account the conductor length, current, conductor size, and conductor material. The NEC provides tables of conductor properties that can be used in these calculations. Fourthly, minimizing voltage drop. Voltage drop can be minimized by using larger conductors, shortening conductor lengths, and reducing the current flowing through the conductors. Using conductors with lower resistance, such as copper instead of aluminum, can also help reduce voltage drop. Fifthly, impact of voltage drop. Excessive voltage drop can have several negative impacts on electrical equipment. Motors may overheat and fail prematurely, lighting may be dim, and electronic equipment may malfunction. Voltage drop can also increase energy consumption and reduce the efficiency of the electrical system. Addressing voltage drop considerations during the design phase of an electrical system is crucial for ensuring optimal performance and reliability. Consulting with a qualified electrical engineer is recommended for complex projects to ensure compliance with the NEC and best practices. Finally, understanding short-circuit calculations is vital for ensuring the safety and protection of electrical systems. A short circuit occurs when an unintended low-resistance path is created in an electrical circuit, causing a large amount of current to flow. This can lead to overheating, fires, and equipment damage. Short-circuit calculations are used to determine the magnitude of the fault current and to select appropriate overcurrent protection devices, such as circuit breakers and fuses. Firstly, understanding short circuits. A short circuit can occur due to various reasons, such as insulation failure, accidental contact between conductors, or equipment malfunction. The fault current can be many times higher than the normal operating current, causing rapid heating and potential damage. Secondly, importance of short-circuit calculations. Short-circuit calculations are essential for selecting overcurrent protection devices that can interrupt the fault current quickly and safely. The overcurrent protection devices must be able to withstand the thermal and mechanical stresses caused by the fault current. Thirdly, calculating fault current. Fault current calculations involve determining the impedance of the various components in the electrical circuit, including transformers, conductors, and equipment. The available fault current at the service entrance is typically provided by the utility company. Fourthly, selecting overcurrent protection devices. Overcurrent protection devices must be selected based on the calculated fault current and the interrupting rating of the device. The interrupting rating is the maximum fault current that the device can safely interrupt. Fifthly, coordination of overcurrent protection devices. It is important to coordinate overcurrent protection devices to ensure that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. This involves selecting devices with appropriate time current characteristics. Accurate short-circuit calculations are crucial for ensuring the safety and reliability of electrical systems. Consulting with a qualified electrical engineer is recommended for complex projects to ensure compliance with the NEC and best practices. In summary, performing electrical load calculations requires a systematic approach that considers all relevant factors, including occupancy type, connected loads, demand factors, voltage drop, and short-circuit protection. Following the NEC guidelines and consulting with a qualified electrical engineer are essential for ensuring the safety, reliability, and efficiency of electrical systems.